Okay, so in this first part, I've split my talk in three parts. The first one is dealing with air and equivalent fluid. So equivalent fluid is when we assume that we have a rigid and motionless skeleton. So we only look at what's inside the air, okay? But the air has a tortuous path because it has to go through the porous materials, and we have this skeleton. This skeleton is in fact the second part of my talk, but I only have one slide in it. Because a lot of some of the important stuff related to this skeleton will be discussed by Fabien in the next talk. And finally, I have some slides about porous materials when we take into account the fluid phase and the skeleton. Okay, so we can also have the skeleton moving. You can, so on these slides, you can follow them if you go to APMR website. Okay, so just have a look at this address. You can follow this on a laptop, on tablets, and also on mobile phone. And if you click on this, you will find a link where you will see these slides. And in these slides, this is only what you see there is only a small part of the slide, because if you scroll down, okay, there's sometimes some explanations about this slide. Okay, so if you go and follow me directly on the website, you will have this slide and the explanations which are below. So by the way, in the explanation of this talk, so one is the fact that what you will see is a long time collaboration with François Xavier and Fabien. And if you want to move from one slide to another, so you have two techniques. Either you use the arrow if you have a keyboard. If you don't have a keyboard on mobile phone or tablets, there are some very tiny, small arrows on the top left and right of the slides, and you can just click on them or tap on it, and you will go to the next slide. Okay. Yeah. So. First line is something very, very simple, okay, but next will be a bit more complicated. In this first slide, I would just want to show you what's going on when you have a wave in a fluid. So it's a compressional wave. So the motion of the particle are like this, but usually we don't show the motion of the particles. The particles are in fact a bunch of air molecules, so oxygen and nitrogen molecules, and a particle is the one dot like this, and you can see if you follow on that we have a wave traveling through the fluid, but our particles are just moving around a fixed position. So usually we show we prefer to show the pressure profile, which is appeared here in red. And of course, if we have a lot of molecules on or particles on the same area, we have a higher pressure, and we have a lower pressure when we have less particle on a very small area. Okay, so this is very basic. And what is interesting here is that you will see sometimes some text in blue or red, or even maybe I think orange. And when you have some text in blue like this, if you have a keyboard, just go on there, click, and you can drag. Okay, and I don't have the sound no more. Oh, sorry, don't know why. Okay, so sound is not working there, but you can have it plays a sound with the frequency that we are studying there. Okay. And the amplitude is just like this. Okay, so each time you see that, you can play with the slides. Okay. Okay, so this was a very simple slide, and the second one is a bit more with equations. So how do we get to this wave equation? To get there, we need to make some assumptions and to write some equations. one of them, of this first equation, is the momentum. So sometimes it's called Euler equation, but it's not Euler equation of motion in fluids, because they also had a condition which we do not use there. And we have also a mass conservation. So we have three parameters, three unknowns: the velocity of the particles, the pressure, of course, or at least the pressure, the pressure modified compared to the atmospheric pressure, and the modification, the perturbation of the mass density. So we have a mass density which is rho zero of the mass of the fluid, at rest, so 1.2 kilogram per cubic meter. But when the waves come, as we have seen in the previous slide, we have some modification of the of this mass density, and this is rho prime. So as we have only two equations and three unknowns, we need a new equation which will link everything, and this is a state equation. So we assume that the air is ideal gas with isentropic exchange of temperature. Okay, there's some stuff written on the slides, on the details for the slides, but I will not go too much into the details about this one. And if we merge these three equations, sorry, we can write the wave equation. So in time domain like this, where we can see that we have velocity of the sound speed, the speed of sound, which is c square, and which is in fact rho zero, so the mass density of air at rest, over gamma, which is the ratio of the specific heats, 1.4 for air in usual condition of temperature and pressure, and P0 is the atmospheric pressure, so usually 1 atmosphere. So we deal when we solve our problem, we have this wave equation in time, but usually we had a time dependence of the form of exponential plus or minus j omega t, just to look in the frequency domain, because it's sometimes easier to look at the frequency domain, and our ear are also some kind of frequency filters, so it's maybe not a bad idea to look also at the frequency domain. And here I have introduced the wave number k, which is omega, the pulsation, over c, the speed of sound, which is also 2p over the wavelength of this compressional wave in the air, in free air. What is important here is the fact that for a frequency which go to 20 Hz to 20 kilohertz, so which is the frequency range of the audible frequency range, at least for babies, the wavelength goes from 70 meter to 0.070, so it's 1 centimeter, 1.7 centimeter. So this explains that it will be difficult to absorb sound or to isolate a room from sound with a partition which is only some centimeter thick, because at low frequency we have a phenomenon which has a wavelength of 70 meters. Okay, and it can't see, or it won't be stopped with something which is only some centimeter thick. I've not detailed how to go from the three equations and then and also how we get these three equations to the this equation of wave. But if you want to do so, I will add this to the website in a few hours. It just only have the explanation in French, so I will try to translate this in English, and then I will add it to the slides. Okay, so when we have oh, sorry, I try to do a lot of stuff in the same time and it's not good, and I just lose my slide on my phone. Not so good. Okay, anyway, when we have when we want to solve the equation of the wave in not free air this time, but for example in a narrow tube, so it's some kind of very basic porous materials, we will need to rewrite some of the equations. So first we can keep the mass balance, okay, so there's no change on that. Then we will need to account for the viscosity of our fluid. So now the fluid is viscous, while in the previous slide it was not. For free air we can just get rid of the viscosity of air. It's too small to be taken into account usually. So here we have Navier-Stokes equations. This is a linear version of Navier-Stokes equation. For the temperature, because every time we have compression and dilatation, compression, dilatation, we have also a wave for temperature. So we need to take into account the equation of temperature, which is Fourier equation. And finally, we have more unknowns than the number of equations, so we need again to add a state equation. Okay, and this state equation just says that the air inside the porous material, we assume that it's again ideal gases, but this time we have also some effect of the temperature. Okay, so this is why it's not the same equation that previously for free air. And we can add, of course, boundary conditions to solve this set of equations. So the boundary condition are the fact that we have no velocity at the boundary with the air inside this narrow tube and the skeleton or the solid part of the narrow tube. And we have also zero temperature variation at this interface, because we assume that the skeleton will stay at the same temperature. Okay, it will stay at the temperature of the room. So when we have the wave passing through the porous material, we have a wave of temperature, of heat at least. So we can have exchange between the skeleton and the air, but the skeleton will stay at the temperature of the room. So no temperature variation compared to the room temperature. Okay, if you want to solve this, it will be complicated like this. So Kirchhoff solved this, but for very simple geometries like narrow tubes, and it was too complicated to solve it for other geometries than narrow tubes. So the only way, except that using finite element methods or numerical methods in a general sense, you need to make some assumptions if you want to solve this analytically. And one assumption is to consider that the flow is incompressible. Okay, so this is not obvious because you are dealing with Navier-Stokes equation, but you will imagine that the flow is incompressible at a larger scale. So you remember this particle moving? Okay, so at the scale of a particle, you can say that the flow is compressible. But if you look at some of the particles, you can see that, okay, we can almost say that the fluid is incompressible if I look at a larger scale. If you do so you have a condition which is div of the velocity which is equal to 0, and then solving this set of three equations just gets you the three uncoupled wave mechanisms. So one of these wave mechanisms is a pure compressional wave propagation with a wavelength lambda and a velocity c. We will get into the details later. We have a diffusive mechanism of Viscous. Okay, just get the deviatoric stress away. So we will have some diffusion effect for the viscous effect, and we will also have diffuse mechanism for the thermal effect. And when you solve the, just the only difference between these two slides is the fact that, this time I introduce the fact that we have the wavelength lambda, for the diffusion mechanism for viscous effect, we introduce a boundary layer which is delta V, and for the thermal effect, we introduce a thermal boundary layer delta T. And when you solve this, you get this wave equation. This time I only focus on the frequency domain. So I think that this is where I make some typos in the slides you have in the printed form. I should not use I don't remember. I should not use the equation what I've written on the PDF file that you have printed. There's some typos in it, so just drop these equations and keep the frequency domain equation, which is this one, which is in fact Helmholtz equation. So the same equation that we have in here, but this time, so the wave number is always omega over c, but c is this time not the square root of k, the compressibility, so gamma p0 over rho. It's the square root of a quantity that we will call the bulk modulus, which is k tilde ek, over a mass density, which is this time also called rho tilde ek. So k tilde ek and rho tilde ek are complex, to take into account the dissipation, and they are frequency dependent because we have some dispersion mechanism. So we have exactly the same equation than in free air, but this time we have like a mass density which is frequency dependent and a bulk modulus which is also frequency dependent. Bulk modulus is the it's like the when it's the modulus for compression. When you compress the air, it will behave like a spring, but a very strange spring with behavior depending on the frequency. So if you are curious about how to get this equation from the three ones I show you, you can have a look there, and I've put everything. So in free air it's quite easy, but I will add it. And for sound propagation in a porous material with a rigid skeleton, like this one, you have everything written on the slide. In what I've introduced just a minute ago, there was this viscous boundary layer delta V. We can get its expression, which is square root of eta is the dynamic viscosity of air, so it's a quantity related to the air properties. Rho 0, it's again the mass density of air at rest, so 1.2 kilogram per cubic meter, and omega is the pulsation. And we can also put another quantity, which is the Reynolds number, beta, which is the ratio of R, the radius of a pore, like this one. So here we have the skeleton in black, so the rigid part in black, and we look at what is the velocity profile inside this duct, this narrow duct, when we have a wave propagating through this. And so beta is the ratio of R over delta V, the viscous boundary layer. So when we have a radius of value R like this, at a frequency of 20 Hz, we have a value of this viscous boundary layer, which is 346 micrometer. But we can change, and the value of beta is close to 1, so the Reynolds number is in its very low values. So we have a very viscous flow. But when we increase the frequency, so when I increase the frequency, I will change the velocity profile from low frequency regime, beta equal 1, to beta equal 10, it's intermediate frequency regime, to a high frequency regime where beta is almost equal to 100, and in this case I don't have a viscous flow, I have a inertial flow. Okay, the boundary layer is reduced to a very small quantity, and so the velocity is almost the same through the whole section of my pore. Okay. Okay, we can also, of course, change the value of the radius, and it will change. Oh no, take exactly the same one. It will change the regimes that you can attend. Okay, so it means that if you want to have some dissipation, so we have dissipation when we have a boundary layer which is quite high, which is close to the value of R, the radius. Okay, if we want to have some dissipation, we just need to have a given value for the radius, and I think I've put, yeah, I've explained this there. So in the frequency range, sorry, if you want to have some dissipation, you need for viscous effect to have a value of the radius of your pore between 11 micrometer and 350 micrometer. We have exactly the same thing happening for thermal effects, okay? But in this time, this is not the profile of the velocity, this is the profile of the excess temperature. And if you look at this and you play with the equations, you will see that to have dissipation using thermal effects, you will need a pore radius which is between 13 micrometer and 410 micrometer. This is when you want dissipation in the audible frequency range 20 Hz to 20 kilohertz. Okay, so it means that if you want to have dissipation in porous materials, you need to have pores with radius of almost 10 micrometers to 500 micrometers. There is no way you will get dissipation using visco-inertial effect or thermal effect with smaller pores. In this case, with smaller pores, the viscous boundary layer is so high that you have difficulty for the flow to go through the materials. So it's like, it's not impervious, okay? You have reflection, so no dissipation inside the pore. If the pore is too large, I think we have something there. Yeah, if the pore is too large, like this one, this material, it's too open. So the viscous boundary layer and the thermal boundary layer are very small compared to the value of the radius, and you don't have dissipation, or this dissipation is so small because it's very limited in a very, very small area, so you have low dissipation. And in this case, this material is not you can't get acoustic absorption in air for this kind of material. Okay, when you change the fluid, of course it will change the value of ρ0, of eta, and so maybe this material is good for absorption, but in water, but not in air. Okay, so this is why you have all the porous materials for air have pores between 10 micrometers and 500 micrometers. Okay, so sorry to being long on this one, but it's just important to show that. And so when I solved the equation of motion in this narrow tube, I also introduce what I call the dynamic mass density, or the mass density, or I will say dynamic mass density, rho tilde ek. Okay, and I said it's a complex and frequency dependent value, and the bulk modulus k tilde ek, which is the spring effect. So the bulk modulus of the air inside the porous material. In fact, rho and k give a general description of the sound propagation in the porous materials. It's like when maybe you are more familiar with the characteristic impedance, ZC, or the wave number, small k, but you can get all this from one, so you can get the wave number and characteristic impedance from the mass density and the bulk modulus, and you can also get the bulk modulus and the mass density from the impedance and the wave number. Okay, but it will be better, at least this is my opinion, it's better to look at rho and k, because rho is related to all the viscous dissipation, visco-inertial effects, and k is linked to the thermal dissipation effect. Okay, so you have two quantities which are clearly separated. You can compute one separately from another, and one is responsible for the viscous effect, for the visco-inertial effects, and the other one for the thermal effects. Yeah, I speak of this a little bit in the explanation. I don't know if some of you are following on the web, or it's too boring. You prefer to look at me? Oh, okay. So when I talk about this mass density, and I will talk a lot about the mass density and the bulk modulus, okay? Because you will see that at the end it's quite easy to, even if you want to take into account the elastic part of the material, you will see again rho and k somewhere in the equations. So when we have this mass density and bulk modulus, we can set limits, asymptotes of these quantities. So for the mass density, rho tilde h, we know that at low frequencies we have a viscous regime. So we have large viscous boundary layers. It's the previous slide. But we know also that we have a velocity in the skeleton which appears in black, which is 0. Okay. And so we can say that the low frequency asymptote of the mass density is rho 0, the mass density of air at rest, so 1.2 kilogram per cubic meter, times a quantity, which is the parameters that we will discuss a little bit later, which is alpha 0, over phi, and phi for me is the open porosity. I will get back to these parameters in a few slides. At high frequencies, we have inertial regime, so the viscous boundary layer are very thin, and the velocity profile is almost constant over the cross section of the pore, because we have only dissipation in a very, very small area, where we go from a velocity which is something not equal to 0 to a velocity equal to 0 at the interface with the skeleton. Okay, but this change of velocity is very, very quick in a very, very small area, so we have very, very small dissipation. And we can, when we deal with the equations, we can see that the high frequency asymptote of this mass density is rho 0 times another parameter I will get back in a minute, which is the tortuosity alpha infinity, sorry, over again phi, the open porosity. Okay, the question is what's going on between these two asymptotes. Okay, and we'll see this in a minute. For the thermal effect, so we have a bulk modulus k, which go from a value of P0 over phi, so P0 is the atmospheric pressure, so 1 atmosphere, for example, over phi, the open porosity, to gamma P0 over phi. Gamma is, again, the ratio of the specific heat, so 1.4 for air. At low frequencies, this value is the isothermal limit, and at high frequencies, this value is the adiabatic limit. Okay, so we go from hydrothermal regime to adiabatic regime, and in between, we don't know yet what's going on. Okay, so it's maybe too small on the screen, but you can find this slide on the web, and you can zoom in to look at it. So if we want to have complete description of what's going on inside a narrow tube. So we solve the equations, and we can also get the exact expression of the mass density ρ and the bulk modulus K, which are this one. Okay, so I just show you what's going on for a circular perforation. So it's cylinders with a circular cross section. So we have an expression of ρ, which is this one, an expression of the bulk modulus, which is this one. I'll put the reference. Yeah, I think the expression are coming from Zwicker and Kosten. Okay, the two guys who said, okay, we will not need to get Kirchhoff all theory. We will compute independently ρ and independently K, and we will see if it's okay with Kirchhoff equation or not. And it was almost okay with only a very few difference. So say, okay, we will always compute K, compute ρ, and almost have Kirchhoff complete equation. Or maybe this one, the dynamic mass density, is from another guy who inspired the work by Zwicker and Kosten, which is Crandall, who published his work in 1923. Okay, he published this, and he said, I will not look into the details about the bulk modulus. I will just assume that the bulk modulus is equal to gamma p0 over phi, or something like that. And Zwicker and Kosten said, okay, we will take into account the thermal effect. So in air, we need to take into account the thermal effect and the viscous effect. In water, sometimes you can get rid of the thermal effect because they are so small compared to the viscous one that you can just forget about this thermal effect. If you have a slit perforation, so in this case you have another expression for ρ, another expression for K. It's the same thing if you have cylinders but with a triangular cross section, where you have an expression for ρ, another for K, and for rectangular perforation, so cylinders but with a rectangular cross section, you have again ρ and K. And the fact is that some people see in this equation that there's a common scheme. Can you find this common scheme? Okay, I will go directly to the next slide. So there's a common scheme in this expression, and the fact is that we can write, sorry about that, but sometimes I write ρ, sometimes ρ tilde ek. So here ρ is ρ tilde ek, and K is K tilde ek. So we can see that we have ρ equal ρ0 over phi times 1 over a function h, okay? And if we have an expression for this function h for a pore geometries, K is given by this expression with again h of pr times omega, okay? Where pr is the Prandtl number, okay? Okay, I have not explained this, but pr is a Prandtl number. So as an example of these people who see that, for example, you can look at the work by Keith Attenborough. Okay, he was one of the first seeing that, okay, seeing this common scheme in the equations. When you want to go a little bit deeper, okay, you want to look at these equations, and you say, okay, so we can have a common scheme between all these pore size, pore geometries, sorry. But it's not so easy. We can try to solve another trouble, okay, for just to explain between the asymptotes for ρ, okay. You remember ρ we get from one value at low frequency to another one at high frequencies, and we have the same for the bulk modulus. We get from one value to another one. So everything is in this h function. But we can go a little bit deeper, and this is the work by Johnson, Koplik, and Dashen. They get a little bit deeper, writing the function h using another one, which is called here function f. Okay, just don't remember the name of the function. What is funny is this slide. So they try to get what's going on between the asymptote value of rho, okay, and the asymptote value of k. So they get a function f. Okay, they were only dealing with rho, okay, but we'll stick to rho now. They were dealing with rho, okay, with asymptotes, and they say, okay, we have a value of this function f, okay, which is 1 at low frequencies, at 0 frequencies. 0 is not a physical value in physics. And at high frequencies, we have an expression for this function f, which represents the dynamic mass density. So they have these two asymptotes, and they said, what's going on in the middle? Okay, we don't know. So this is why a miracle occurs. And they said, if you look at their papers published in 87, they said, okay, the simplest function which go from this value to this value to us is this one. Okay, they have some conditions about the pulsation power. Okay, we know that we have some dependence of the frequency, which is of the order of something like this half power of the frequency, but otherwise they just created this function and that's it. There's only a few people who understand that, and this is probably why the models are called phenomenological. If you take the book by Jean-François Rondeau and know the book by Jean-François Rondeau and Noordin, the second version, you will see that everywhere it's written phenomenological model. It's called like this because this guy just take a function and okay, it was working, but there's no explanation behind this. Okay. So we end up with, once we have this function f, it was for the mass density, so we get the expression of rho, but not for a given morphology, but for any morphology you want. Assuming that you know some parameters, okay? We need to know some parameters. So sometimes the parameters are equal to the radius of the perforation when we have a circular perforation, or it's equal to the half length if we have, for example, a slit or something like that, okay? So all these parameters, which we can see in rho tilde x, for example, we have alpha infinity, we have phi, of course, the open porosity, we have sigma, the static air flow resistivity, lambda, the viscous characteristic length. I will explain this in a minute. You compute your value of these parameters for your geometry, or you get them from measurements, and then you use this function, where here we can find the function f, okay, and you get the mass density for all the frequency range. So this was the work by Johnson, Koplik, and Daschen. And then there was a work, so 4 years later, by Champoux and Allard, who just applied the same thing. So the same miracle occurs, but for thermal effects. Okay, so they said, okay, Johnson, Koplik, and Daschen use a miracle function for rho, as it seems to work. We will use a miracle function which is almost the same, but for thermal effects. Okay, so they take the asymptotes value and say, what is the simplest function? If we think about it, it's this one, and we have this expression for the bulk modulus, which introduce some more parameters. So one was the thermal characteristic length lambda prime. Okay. And when trying to find a name for these models, I think that it was not fair just to call it Johnson-Champoux, because Champoux was the first author of the work, but Jean-François Rondeau made a lot of works on that. So I finally choose to put Johnson-Champoux-Allard. So when there's two guys, we had the name of these two guys. So Johnson for Johnson, Koplik, and Daschen. Okay, so Johnson et al. And Champoux-Allard just to get Allard somewhere in the model. So Johnson-Champoux-Allard model, so GCA model. It's this one with rho and K like this. Okay. There's lots of model, in fact. Not only the Johnson-Champoux-Allard Lafarge, which is probably the most widely used, but there's a lot of models. These pictures just show you that the more complicated is the geometry of your porous material, the more complicated, the higher number of parameters you will need to describe the geometry, of course. So if you have, if we assume that we have a wave coming from the top, okay, we have a wave coming from the top of these different geometries. So here we have a geometry, another one, a third one, and a fourth one. If the geometry is only straight cylindrical pores, we need only 1 or 2 parameters. And we have models like the one by Zwicker and Skosten. So the guy who introduced rho and K. If we have slanted cylindrical pores, we need to add a new parameters, another one which accounts for this orientation of the pores. And so we have, for example, the model by Mickey with phi, sigma, so the open porosity, the static resistance, the resistivity, sorry, and the tortuosity. If you have pores which are not just slanted but with a smooth variation of the sections, okay, you will need a new parameter, at least, or maybe 2. So here you can find a model by Keith Attenborough, which was one of the first for this kind of geometry, but this parameter B was frequency dependent, so it was not so easy. This is why Jean-François Rondeau won the race for the name of porous materials. There's a fight between Keith Attenborough and Jean-François Rondeau, but I think now they are almost all retired. So they are the best friends again. And so we can have the Johnson-Champoux-Allard model is in this one, but there's another model I will talk in a minute, which is Johnson-Champoux-Allard Lafarge, when we had a new parameter, which is K prime 0. And if you want to deal with pore section with possible constrictions and quickly variation in the pores, in this case you will need a model which is called Johnson-Champoux-Allard Pride Lafarge. I will get back about this. And you need, I don't remember the number of parameters in this. 8. Whoa. No. What? Oh yeah, 8. So you need more parameters because the geometry is more complicated. So if we go to the another model, which is Johnson-Champoux-Allard Lafarge, the only thing that changed is not rho. Rho is exactly the same, okay? But the work by Lafarge et al., so it's Lafarge, Le Marinier, Allard, and Tarnoff, okay? They had a new parameters which is K prime 0, okay? And in this one, so K prime 0 is the static thermal permeability. In fact, it's coming from the PhD thesis of Denis Lafarge, who just tried to get a symmetry between the viscous effect, so in rho, and the thermal effect in K. Denis noticed that in rho we use more parameters than in K, so he tried to add a new parameters in K, because he said, okay, there should be some symmetries between the effects, so there might be some more parameters to describe the bulk modulus a little bit more precisely. And indeed, if you look at the paper by Champoux and Allard, there's already these parameters K prime 0, but they are not naming it like this, and they were just seeing this without understanding what they were seeing. So finally, it's Denis Lafarge who introduced really these parameters K prime 0. And so I decided to name the model Johnson-Champoux-Allard because, okay, we need to get Jean-François Allard somewhere. and Lafarge for Lafarge et al. Okay, so the model is called GCAL. If you are wondering, yes, I've made this nomenclature and I put it on the internet, and then after everybody was using it. And some guys like Steve Wright said, okay, in porous materials, in porous materials it's quite nice because everybody is using the same nomenclature. So if you have very important things you want to spread, put them on the internet. And there were, so the last model I will talk about is the one which is called Johnson Shampoo à la Pride Lafarge, GCAPL model. Okay, why P is before L? It's just because Pride, Delmorgan and Gangi introduced two more parameters, this alpha 0 and alpha 0 prime. They introduced the parameters in 93, so it was the same year that Denis Lafarge published his PhD thesis. So Pride et al. Introduced these parameters, these two parameters, but there were some typo that Denis corrected. Okay, so the name of the model is Johnson Shampoo à la, then Pride et al. For these two parameters, these two new parameters, and Lafarge because of the correction for alpha 0 and alpha 0 prime, and because he also introduced with Le Marinier, Allard and Tarnoff, he also introduced K prime 0. Okay, and in this GCAPL model, so you have a lot of parameters, and it's quite complicated, in fact, to get them from measurements. So guys who are dealing with virtual prototyping or micro-macro approach, like Fabien and Camille, who is at the end of the amphitheater, they can have access to these parameters, but from measurements it's very complicated. Okay, usually we don't have direct measurements of that. We need to get some fitting stuff. Okay, so this is a nice model, and from this model you can get back to the GCAL model, and you can also get to the GCA model. Okay, and even for the GCAL model you can get to the GCA model. Okay, these three models are quite nice made. Okay, so I would like to take some minutes now to discuss about these parameters that I have introduced, because the idea was just we have rho and k to describe the sound propagation in porous materials. We first have asymptotes, then we get a numerical function to get what's going on between these asymptotes. We use parameters. Okay, where do we get these parameters? From measurements, but what are these parameters linked to? Okay, so one answer is in one of these answers are in these slides. So it's not slides about characterization; it's just slide about definition of the parameters. So the first parameter is the open porosity phi. So this is the porosity which connect all pores. Okay, if you have a pore like this one, I don't know if you see where is the pointer. Well, anyway. You have do you see the mouse? Yeah. You have a pore here, which is not connected to the rest of the network. So in this case, we take it into account in the skeleton properties. Okay, we'll say that for example, the Young modulus is a bit lower than the materials if we had not this kind of pore inside the structure. There's also quarter wavelength resonance, quarter wavelength pores, if you want. Some call them dead-end pores, so they are pores which are not connected to the rest. So they can have some dissipation, like quarter wavelength resonators, but they are not exactly part of the main network. Okay, and what we are very interested in is the open porosity, the porosity of the open network. So this porosity goes to almost 0 for perforated plates or facing screens, to 1. Okay, for a melamine foam like this, we have a porosity which is 0.99. And for a perforated plate, I don't know if we have a perforated plate like this. Oh, but I can see a facing screen. For a facing screen like this one, we have a porosity which is probably 0.01 or 0.001. And Noordi-Natala and Fransgaard made a very nice article more than 10 years ago just to explain that this is a porous materials. Even if people think that this is a separate part of materials, okay? In fact, this is almost like this, but with some modification. And I invite you just to look at the work by Noordin and Fransgaard and Noordi-Natala about this. And then after, we have to take into account what we call some end correction, and we have just finished a paper with Fabien Chevillotte about how we can take into account the end correction correctly, because this is a field where people are doing strange things since 70 years, and in fact they are all doing exactly the same thing, and there's nothing new since 70 years, even if people work on that all their career. This is science. Okay. So in this slide, you can, here I show you the real and imaginary part of the bulk modulus, okay? I could also show you the mass density because the phi, the porosity is also involved in the mass density, but I choose to show the bulk modulus because it's maybe easier. And you can play with the value of phi just to show you how it changed the real and imaginary part of the bulk modulus. Okay, so it mainly changed the real part, but as we have causal functions, it's also changed the imaginary part using Kramers-Kronig expressions. Yeah. Microphone. I have the microphone.
I've got just a short question about this porosity. Have you ever heard about percolation? So this principle of you have a say a big forest, and as soon as the density of trees is high enough, a fire would spread from one end to the other end. While if it drops below a critical density of trees, it doesn't. And this usually shows a phase transition, so a very sharp transition between the probability, for example. While here these curves seem to move quite smoothly. Is there a phase transition hidden somewhere at the critical porosity?
Oh, so yeah, for these parameters, it changed smoothly, but there's other parameters, and okay, you can, if you change another one, you will, okay, just let me change something. Okay, you have other parameters, so I would say that there's not only the porosity who is involved in that, in this phenomena, there's more than the porosity, because with the other parameters, you can change and have something which is sharper. Okay. Don't know if it's answered the questions, but I think it's not only related to the porosity.
Just a comment about this question. If you increase the density of closed pores, then you will have this sharp effect. Because you will open some other pores, and then it will percolate if the the phase is not percolating before.
Okay, so this was the first parameter, the open porosity. Okay, so another parameter is the static air flow resistivity. So usually we reduce it to resistivity. And these parameters go from some values where eta here is the dynamic viscosity of fluid, and we can also, we will see there's another parameters, and we have conditions between these parameters, so I put them there. it's just the relation, the static flow resistivity is just the relation between the velocity through a porous materials when you apply a pressure drop at both ends of this porous material. If you want to see the effect of the resistivity, you should plot the real and imaginary part of the mass density this time, because this is a parameters which is related to viscous effect at low frequency, and you can see how it change mostly the imaginary part of the mass density. Okay. Third parameters is, usually we say tortuosity, but it's not correct. We should say high frequency limit of the dynamic tortuosity. Okay, it's a bit long, so we say tortuosity. Johnson complication. So these three guys who have these numerical functions also introduce these parameters, and saying that this is a measure of the dead order inside the porous materials. In fact, so this value of alpha infinity goes to 1. 1 is like when you have a straight cylindrical pore, you have alpha infinity, which is equal to 1. When you have a tortuous path through the porous materials, this value is larger than 1. The more tortuous it is, the higher is alpha infinity. And if we have a look at how it changed, it's quite, it's only changed the real part of the mass density, and I choose to get the same scale for all the plots, so we don't see we don't see a lot of modification, but there's some modification. Okay. It's also changed a little bit the imaginary part, but at the very high frequencies. Okay, so the next parameter is the viscous characteristic length. This is somehow related to the smaller pores inside the porous materials. I will not discuss about this because Fabien has a nice presentation about that. There's some condition, of course, that this viscous characteristic length should be lower than the thermal characteristic length that we will introduce in the next slide. If you want to see the effect of the viscous characteristic length, you just modify this and you get that. Of course, in this simulation, which are done in real time, I've not put the limitation. Okay, I can get a viscous characteristic length which is much larger than the thermal characteristic length. So you need just to think about that. Maybe for some parameters you choose in these simulations, the material is not physical. So the thermal characteristic length is related somehow to the larger pores to the radius of the larger pores inside the porous materials. So again, Fabien has something to present you later, so I will not go into the details. And lambda prime is related to the thermal effect. Okay, it was introduced by Shampoo and Allard, so it's related to thermal effects, and we can see there how it changed the behavior of the real and imaginary part of this bulk modulus. Okay, I probably change this. Oh, sorry. I have to change this. Oh, I need to change this. Okay. Okay, you can see the effects. And finally, the last parameters I will discuss is the static thermal permeability, which play the same roles, the equivalent roles for thermal effect than the resistivity or the viscous permeability plays for visco-inertial effects. Okay, so this time you don't have what is the velocity through the porous materials when you apply the pressure drop, but you get what is the excess of temperature when you have a change of in time of the don't remember the expression. What is the expression? The equation for K prime 0? Anybody is remembering? Or? No? Okay, I'm the only one working today. Okay, so there's it's not the relation between the pressure drop and the velocity. It's between the excess on temperature and the change of the temperature with time. So this one is usually not easy to understand, but I will show you. So if we play with that, we can see its effect, but it's better. We can see the effect better in the next slide. So we jump directly to this slide, where you can play with it there or directly on APMR website. Okay, what you see there is the sound absorption computation. So we using rho and k of a GCAL model. So we have all these 6 parameters plus the thickness of the porous material. And we have normal incidence and diffuse field computed in real time. Okay, and if I change the value, for example, of this static permeability, you can see that it's only a very small change in the curve. Okay, so it's a low frequency parameters, but it's not because it's a low frequency parameters that it's only changed the low frequency. Okay, it can change, for example, the point at which in frequency something will start, some effect will start, so it will influence also the high frequency range. And you can change the tortuosity. So you see that the tortuosity just to move to the low frequency, the first peak there, and this peak is just because we have a quarter wavelength resonance in the of the air motion inside the porous material. You can see the effect of the resistivity. So it should not be too small. Okay, this is not correct because it should not be too small. It computes too fast, too small, because we have the wave go through all the materials without being dissipated, and it should not be too high, because in this case the material is almost impervious, so we have reflection. Okay. Again, in this simulation, I don't put some condition about parameters, so you don't have to, you have to check if your parameters are consistent to be a real materials or not. Okay, if you want, we have 5 minutes and we can play with a little exercise, which is to find the value of to find information about the values of these parameters for 3 different morphologies, so the red, the blue, and the violet one. So for the porosity, okay, so we assume that we have a wave going from the top. Okay, the red, blue, and violet parts are the skeleton, so the rigid parts, and the pores are in white, appears in white. So we have a porosity for this red morphology, a porosity for the blue morphology, which is almost the same because I just reduced the size of the perforation radius, but I kept the same value for the porosity. Okay, for the ratio of the volume of air over the volume of the material. And for this last morphology, we have almost the same porosity. The only change that changed between the blue and violet morphology are that we had some very small chicanes. Okay, so we had just small chicanes. It does not change a lot the morphology of the it does not change the open porosity, sorry, of this morphology. If we want to compute the airflow resistivity, so we have an expression for cylindrical pores with a radius of r and a porosity of phi, and eta is the dynamic viscosity of air, of course. Okay, so we have this value sigma for this morphology. We have this value which is higher because we have smaller radius perforation radius. Okay, so the value of the static airflow resistivity is higher, and in this last structure we have a higher again resistivity because we had this chicane, so the it's harder for the flow to go through the porous material. Okay, for the tortuosity, as I said, if we have straight cylindrical pores, the value of the tortuosity is equal to 1. If we are not dealing with the flow distortion effect. So here it's again straight cylindrical pores, so the tortuosity is equal to 1. And this one we have a tortuous path, so the value of the tortuosity is higher than 1. For the viscous and thermal characteristic lengths, they are equal for straight cylindrical pores to the value of the radius of these pores. So we have these values, okay, which are different between the red and the blue because we have not the same radius. And for the violet structure, we have the value of the viscous characteristic length is related to the radius of the smallest pore, so between a chicane and the skeleton. Oops. And for the thermal characteristic length, we have a value which is almost related to the radius of the larger pores. So when we look at the structure without looking somewhere where there's some chicane. Okay, we can also compute there some values for the thermal static thermal permeability. Okay, and we can also compute, as I said, if you have the morphology, you can compute the value of these last parameters introduced by Pride et al. And modified by Lafarge. So you have these values for straight cylindrical pores, and you have these relation for a more complicated structure. Okay, so I will let you play with this example, with this exercise if you want. This is an exercise I saw the first time when Walter Loix was presenting a plenary lecture during the first TAPM here in the same amphitheater. It was in 2005. Okay, he showed that, and I just thought it was a nice idea. Okay, so this is my only slide in the solid part because there's some more stuff in Fabien's presentation. In solids, so I have not the time to explain the equation and stuff like that, but I think I will add them. If you write the equations and solve them, you will see that you have this time two waves. One is a compressional wave, so this one, and another one is a shear wave. Okay, so this one. So I switch to the biotheory, and I have 15 minutes to finish the biotheory, but it will be okay. So in the biotheory, what is interesting is that Bio in his first work, so it was in the 1940 to 1950s, they just write the equation of the sound propagation inside the porous material, assuming that we have an elastic skeleton. Okay, and in this case, he said, okay, if I send a wave, let's say a wave in a compressional wave in air with an oblique incidence going inside the porous materials, I should have at the end three waves. Okay, three waves because I have one which come from the compressional wave inside the air, inside the porous materials. Another one coming from the compressional wave coming from the compressional wave inside the solid part of the porous materials, and the last one is the shear wave in the skeleton of the material. So people were not agreed with that, or were a bit skeptic about that. And finally, in 1980, so Plona made an experiment. So it was at ultrasonic frequencies in water, etc. So basically, he sent a compressional wave, okay, in a fluid. It was not in air, but it was in a fluid, and he gets two waves at the end, okay, two compressional waves at the end. So he sent it in the normal incidence, so he don't have the shear wave, okay. But they were interested by getting the two waves, the two compressional waves, okay. People were not thinking that we should get two compressional waves if you send one. So you get these two compressional waves. The first one, P1, P for fast, primary. For primary is is the wave which propagates mostly inside the skeleton, okay? The compressional wave mostly inside the skeleton, and P2 is the primary 2, so the compressional wave propagating mostly inside the fluid part. We can't say that one wave is propagating through the fluid and the other one is propagating through the solid, okay? We have interaction between the two, so this is why people don't say this is the wave propagation through the fluid. Even if we think this in our head, okay, they don't say that, but you can think of it. You have a wave propagating mainly in the fluid phase, or take the origin mainly in the fluid phase, and the other one in the solid phase. Okay, so what is interesting in this is that people like Leo Beranek was seeing that when putting a porous material inside an impedance tube, okay, in the 1940s, and he said in one of his articles in 1942, he said, okay, it's quite strange because I send a wave inside in an impedance tube with my porous material at the end, and I get an absorption coefficient like this with a peak like that. And he said in 42, so while Bio was working on his work, he said, oh, there may be a wave inside the frame of the porous material, okay? So Leo Beranek, or people dealing with acoustic porous materials, we are already seeing that, but people from the oil industry and geotechnics porous materials wait for the work by Plona in 1980 to just say, okay, we have 3 waves in a porous material, 2 compressional one, and a last one which is usually called shear or S wave, which is the shear wave. Okay, so quickly, but this is just to show you some equations, and it's the end of the presentation, so I would like to finish with something very nasty. So here is the original Bio expression, okay? In this case, you don't have the Helmholtz equation we have in fluids on equivalent fluids materials. So you have 2 equations, who say that we have a solid part and we have we have a solid part and we have a term which is related to the interaction with the fluid, okay, and we have another part which is mainly deal with the fluids, okay, and we have a source term which is related to the solid part, okay, to the motion of the solid part. So in his first mathematical expression, Bio used the displacement field of the solid part, US, and the displacement field of the fluid, so UF. So okay, you have the reference there, and there are some parameters that people work and publish some stuff just to explain what are these parameters, how we compute them, okay. But in fact, there's more than one formulation of Bio theory. There's many. So this is the original, we call it USUF formulation. There's also another one introduced by Bio a little bit later in 1962, just for anisotropic materials. So he used US and W. W is a function of UF and US. Then after, people dealing with theory were using US and P. It's better to think with P for the pressure than fluid displacement, okay. But for a numerical model, it was very important to get a US and P formulation. And this is what Nourdine Atala managed to get with Raymond Panton and Patricia Deberg in 1988. Okay, and it reduced the number of degrees of freedom in a finite element code. So you get from 6 degree of freedom to 4. So you reduce the number of unknowns, and so it's better for your computation. There's also another one, formulation by Olivier Dazel, introduced in 2007, who is interesting when you want to write for only if you want to deal with analytical formulation, it's easier to write the wave numbers using this formulation. Okay, so the important point of this slide just to show you that there's multiple ways to deal with biotheory. Oh, I don't want to translate. It's okay. So in the UP formulation, that I said that people dealing with only analytical expression used a long time ago, like Guy Bonnet in 1987. Okay, we also have Claude Boutin, Guy Bonnet, and I don't know who is bad. And then after we had the final introduction with Atalap and Thunderberg. And this expression you see there when you get rho and k, okay? The rho and k I was talking about is from this publication with 3 unknown guys. Beko is François Xavier, of course, and Olivier Dazel, and me. Okay, and in this one, we just modify a little bit. This is not rocket science, in fact. We just modify a little bit the expression just to make appear rho and k. So then after you get rho and k. The first one we compute without dealing with the elastic skeleton. Okay, we compute rho and k. So with the pore size morphology, we get this. We put this in these equations. We solve these equations. And we get the motion of the wave propagation in our porous materials with an elastic skeleton. Okay, and in this case, we assume that this is elastic modification, elastic motion. So there's no big motions of the skeleton, so that you can say that rho and k you computed assuming that the skeleton was motionless can also be applied when you have a very small motion. Okay, we are not talking of stuff like that. Okay, just very small motion, like you put this in the impedance tube, or you put this somewhere and you are talking close to it. Okay, so the best part of this bio stuff, because I only have 7 minutes to finish, is this document. Okay, so you can get access to this document again on the slide, but it's much more. I will just show you the document. So you can change the thickness, and you have 2 computations. One is, so no, I think that you will, and I hope that you will use the correct nomenclature, not because I've introduced it, but because everybody is using it. So the correct nomenclature is Johnson Shampoo à la Lafarge model. Okay, so this is rigid skeleton. If you would like to add the effect of the skeleton, you should say bio Johnson Shampoo à la Lafarge. Okay, so bio JCAL to reduce it, because you add the elastic effect. When you put bio before something, it means that you take into account the motion of the skeleton. Okay, so here in blue I have the parameters for the GCAL, rigid skeleton, and in red I have the parameters for the elastic skeleton. Okay, so it's the mass density, Young modulus, Poisson ratio, and loss factor. Here I'm assuming that my material is isotropic, of course. And you can see, for example, that one important point is that if you have high resistivity material, okay, the impact of on the sun absorption, for example, but it will also be the case for sun transmission, it is very important. Okay, we have very high difference between the blue and the orange curve, while when we have low resistivity, so if we take the value for a melamine foam like this, okay, a bit more resistivity, you have some effect of the resonance of the motion of the skeleton. Okay, but it's quite small. But if you increase the resistivity, the impact might be very important. So it's sometimes very important to take into account this motion of the elastic part, even if you are doing absorption and not transmission, because you can have stuff like this, and you will not understand if you only take a rigid skeleton model like GCAL, GCA, GCAPL. Okay, and just before finishing this, I will try to open. Okay, I'm new to Windows, so sometimes okay, no, it's not that. Okay, anyway, I will try to. Can I? No, I can't. Oh yeah. Okay, so if you go to APMR, you have the same thing with different colors, but okay. And then after I explain you with a MATLAB GNU Octave code how to compute the sound absorption in normal incidence. Okay, so you have all this code there, okay, to make the computation for normal incidence with Bio GCA L model or Bio whatever model you want. You just change rho and k and you put this in the equation somewhere in the code and you have Bio what you want model. Okay, just go back to one slide. And this is using the last formulation by Olivier Dazel, François-Xavier Becot, and myself. And finally, because I'm good on time, this is my last slide. And if you, I would be interested to have some feedback about that. So I just put some proposition, but you can write what you want, okay? Because it took me a lot of time, and what you have seen is only a small part of what I've made, because as you have seen, there's some explanation sometimes on most of the slides, okay? Okay, that's the end of my talk. Thank you for your attention.